Assalamualaikum dear students. This is our fifth lecture of group 3-2. Last time we were discussing number of elements in a conjugacy class in Sn and in An. I mean the symmetric group Sn of degree n and the alternative group of even permutations. Last time we were using a little bit of number theory to calculate the number of conjugacy classes. Here we have another alternative way which is quite easy. Those who have not a good grip of on number theory, they can solve this equation relatively. It's easy to solve rather than that reduction formula we were using from the partitions. So what is that technique is, suppose a permutation alpha of degree n is decomposed into disjoint cycles. If there are first at all you have a permutation of course from Sn, and you can of course decompose this permutation into cycles, and if there are kr cycles of length r, this is the technique. If there are kr cycles of length r, mean you have k1 cycles of length 1, k2 cycles of length 2, k3 cycles of length 3, and of course kr cycles of length r, where r is equal to 1 to 3. With the understanding that we are using kr is equal to 0 if alpha contains no cycle of length r. Suppose you have no cycle of length 3 in its decomposition, then we will take k3 is equal to 0. Okay, because here kr cycles of length r. Suppose you have no cycle of length 3, then k3 must be 0. This is our understanding. Then the number of conjugacy classes in Sn is the number of non-zero integral solutions of the equation. This is also a type of Diophantine equation. Again, you have to use a little number 3. However, without number 3, you can also solve this equation, because with the help of some trial methods, of course, you can solve this equation. You need to be a little intelligent. Okay. For example, I want to find number of conjugacy classes in Sn. You know that we have solved this problem, and we know very well that there are 7 number of conjugacy classes. Now, how can you find that there are 7 number of conjugacy classes in S5, and how can you write their types of permutation, and then with the help of types of permutation we can also write the corresponding elements and the corresponding decomposition as well. Okay, so suppose you want to solve this for n is equal to 5. Of course, since a cycle of length r must contains r elements, that's why this is very obvious that k1 plus k2 plus 3k3 plus 4 and so on must be equal to n, right? Where n is the degree. Here n is equal to 5, because we want to discuss permutations of length 5 of degree 5, mean S5, and we want to know with the help of this equation that how many conjugacy classes we can find in S5. So the idea is to find number of solutions. Okay, so here we have the number of solutions. You can start from 5 if you put k1 is equal to 5 and take all other zeros, 0, 0, 0, 0. You see this class. We are taking k1 5 and suppose there is no cycle of k2, there is no cycle of k3, length k3, there is no cycle of length k4. Okay, for this particular S5, this equation becomes, we can write this equation as, where is my cluster? Oh yes, it is. For n is equal to 5, we have k1 plus 2k2 plus 3k3 plus 4k4 plus 5k5 is equal to 5. This is our corresponding equation for k5, and we want to find number of conjugacy classes in S5 with the help of this equation. So this is one solution. To write k1 is equal to 5 and put k2 0, k3 0, k4 0, k5 0. So this is equal to 5 plus 0 plus 0 plus 0 plus is equal to 5. This one. Now, what is the meaning of this understanding? That there are one cycle of k1, length k1, k1 cycles of length 1, because here the coefficient is 1. Of course, this coefficient is 1, its coefficient is 2. Suppose there are k2 cycles of length 2, there are k3 cycles of length 3, and there are k4 cycles of length 4. Now since k1 is equal to 5, here k1 is equal to 5, you see k1 is equal to 5, this means that there are 5 cycles of length 1. This is the first position. This is the first position. This is length 1, length 1, length 2, length 3, length 4, length 5. So when I am writing this 5 tuple, I am saying that there are 5 cycles of length 1, because the coefficient of k1 is 1. So k1 is the, what we are saying, kr cycles of length r, right? Kr cycles of length r. So we have k1 cycles of length 1, that is we have 5 cycles of length 1. So from here you can write its type. This is in fact 1 plus 1 plus 1 plus 1 plus 1 means 5 cycles of length 1. This is equal to 5. This was the corresponding partition. This is one partition. So the number of solutions of this equation is in fact the number of unordered partitions of 5, which was in fact is equal to 7. So we will prove that we have 7 number of non-zero solutions of this equation. The rest of the work we already have done in our last lecture, so you can see that lecture. Now I just want to relate that yes, I am at the point that there are 5 cycles of length of 5. So the what is the type? So this, the type is the identity. This is the identity. Type is the identity permutation. The secondly, there is a second solution is now if you put 4, we cannot find 5. 4 and here 1, then this must be 6. So you cannot substitute 4 for k1. So but if we write k1 is equal to 3 and put k2 is equal to 1, this would be 5 and all others are 0. So there is another solution is corresponding, if you put k1 is equal to 4, we cannot write sum as 5 in integral solutions. So that's why we will write k1 is equal to 3. So you can write k1 is equal to 3, then put k2 is equal to 1, then 0, 0, 0. This is another solution. What does it mean? This means that you have one cycle, 3 cycles of length 1, this is length. This is length. So here K1 is equal to 3 and K2 is equal to 1. You know, 3 plus 2. If you put 1 here instead of K2, 3 plus 2, 5, and all rest of the coefficients are 0. So this is equal to 5. So what we are getting? We are getting 3 cycles of length 1 and 1 cycle of length 2. Right? K1 cycles of length 1, K2 cycles of length 2. So in this solution, we are getting 3 cycles of length 1 and 1 cycle of length 2. That's why you have 1 plus 1 plus 1. These are the 3 cycles of length 1 and 1 cycle of length 2, which is equal to 2. So answer is 5. Of course, you have the permutation type is 1, 2, because these are corresponding to the identity, and this is equal to 1, 2 cycle of length 2. So 1 cycle of length 2 and 3 cycles of length 1. Now next solution is, instead of write 2, if you write 2 here, 2 into 2, 4, it would be difficult. 2 plus 2, 4, then you cannot find 5. So write 1. Okay? If you write, oh no, you can find K, you can set K3 is equal to 1. 2, 0, 1. Yes, you can have sum as 5. So the solution is, put here 2, then put here 0, then take K3 is equal to 1. This is 1, and then 0, then 0. Right. So this will give you 1 plus 1, 2 cycles of length 1. Here K1 is equal to 2 and K3 is equal to 1. So that's why K3 1 means 1 cycle of length 3. 1 cycle of length 3. This is 1 plus 3. This is equal to 5. And this is in fact 1 cycle of length 3 and 2 cycles of length 1. Of course, cycle of length 1 are identity elements, and cycle of length 3, this is equal to 1, 2, 3. This is the type of the permutation, right? Also you can write type of the permutation. Now, then you can put 1. There is no other solution for 2. Then you can put here 1. If you write 1, then you can put here 2. You can take K2 is equal to 2. So 1, and there are 2, 2 and 2, 4 plus 1, 5. Then 0, 0, 0. Yes, you can take K1 is equal to 1 and K2 is equal to 2. This means that you can have 1 cycle of length 1 and 2 cycles of length 2. This is length 2, 2 cycles of length 2, 1 cycle of length 1. So what does it mean that this is 1 plus 2 plus 2, 2 cycles of length 2. So what would be the type? Type would be a 1, 2, 3, 4. This is the type of the permutation. Yes, they will form another conjugacy class. This is another conjugacy class. So these are the conjugacy classes. We are getting the conjugacy classes, and all elements which are conjugates in one class, their type. These are the types. So even from this equation, you can have the partitions, possible partitions, you can find the sum, okay, and you can have the possible types and even the number of conjugacy classes. Okay, then there is another way. You put 1 and K4 1. Take 1, 1. What is this? This would be 1, 0, 0, then take 1, then 0. This means that 1 cycle of length 1 and 1 cycle of length 4. So this implies 1 plus 4, this is equal to 5. So the type must be 1, 2, 3, 4. Right. This would be the type. Then here I am writing k1 is equal to 1 and k4 is equal to 1. This is the solution. Okay, there is no other solution for 1, so you can now set k1 is equal to 0. We set k1 is equal to 0, and then you take 1 k2 and 1 k3, you will get 5. Yes, you can have 1 1 and then 0 0. This means that one cycle of length 2 and one cycle of length 3. This means that you are getting 2 plus 3, which is equal to 5. So type must be 1 2 3 4 5. This would be the type. Right? You have 1 2 3 4 5 6, and there is another. All you put 0 and then k5 is equal to 5. So here k2 is equal to 1 and k3 is equal to 1, and lastly you can have 0 0 0 0 and then 1. This means that 5 is equal to 5. So the type must be 1 2 3 4 5. This would be the type. These are the types. This is the seventh type. This is the type. This one is the type. This one is the type. You have this type, this type, this type. You see, there are 7 types. 1 2 3 4 5 6 7, and the solution is you are taking k5 is equal to 1. Now try to solve this. You cannot find any other solution, any other integral solution, non-zero integral solution, because here this 1 indicates the length and k1 is the number of solutions. That's why you cannot substitute the negative integers, because k1 is the number of kr cycles of length r. Okay, the coefficient is the length, and length should be positive, right? And here kr is the kr cycles of cycles, kr cycles. Of course, again kr cycles could be there. You may have a 0 kr cycles, 1 kr cycles, 2 kr cycles, but you cannot have minus 1 kr cycles. That's why you cannot have minus 3 length. That's why both are positive, so there is no question at all to substitute. Like you suppose that if you substitute 3 here, 2 into 3 6 and minus 1 here, no, you cannot substitute this, because kr cycles of length are kr cycles. These are the cycles. So of course cycle of length k1 cycle, k2 cycles. How many cycles? Number of these. Kr is the number of cycles and r is the length of cycle, and both are of course non-negative, right? 1 may be 0, kr may be 0, but r must be a positive integer. That's why. So this is another way to count the number of conjugacy classes in essence. So yes, since you have taken n is equal to 5, and corresponding to this equation we have solved all the possible solutions, and corresponding to this solution we are getting the partitions, and corresponding to this partition you can write the types, and corresponding to types you can write the number of conjugacy classes. So there are 7 conjugacy classes in S5. Now we have another way to find number of elements in a conjugacy class. Okay, yes, we have a theorem for this one, that number of elements in a conjugacy class is equal to index of the normalizer of the representative element in G. Yes, now we want to solve this theorem, and we will see that even with the help of this theorem, means you take an element A, then find its normalizer in G, and then find the index of that normalizer. That would be the number of elements corresponding to the in the conjugacy class of the element A. Yes, first we have a theorem. Okay. Okay, now we have a theorem that this is a liter for size of a conjugacy class Okay, what is this theorem? This theorem is the number of conjugacy class, the number of elements in a conjugacy class CA of an element A in G of an element A belong to G is equal to the index of its normalization is equal to the index of its normalizer in G. You take an example of S3. Say, S3 is A, B, A cube, B square. And if in permutational form you can write alpha, beta, alpha cube, beta square is equal to AB square is equal to E, you know very well. This is in fact E, A square, B, A, B, A square, B. Now, you take an element A, say for A, we need to find CA, and CA is A square, we have discussed in detail. Now find the normalizer for A. What is normalizer? So normalizer of G in A, this is equal to, in fact, those elements of G belong to G such that G is equal to AG. And one should know that if you have just one element, then corresponding to one elements, both normalizer and centralizer are always same. Okay? This is also the definition of centralizer for single element. But in general, there is a difference between normalizer and centralizer, because in normalizer we take those elements which permute with every element of that set for which you are finding the normalizer. However, in centralizer you are taking those elements of G which commute with every element of that set for which you are finding the centralizer. But if you have just one element in your set, then its centralizer and normalizer both are same. There is no difference. That's why I am writing G is equal to AG. I can write without any hesitation, because you have just one element and I want to find the centralizer of one element, right? So G, those elements of G which for which G is equal to AG, and you know that if you find normalizer of A in S3, so those elements of G belong to S3 such that GA is equal to AG. So can you find the elements which are commuting with this A? So there are three elements. Of course, one is E, EA is equal to A, and then A itself, A square is equal to A square, yes it is, and the third is A square. And also we know that normalizer is a circle and centralizer is a circle. Yes, it is a circle. Okay, so what is the index of this normalizer in S3, which is equal to 2? So the index of, the symbol is index of this normalizer of A in S3, this is index of H in G. Index of, you know by Lagrange theorem, both order and index of a finite, of a group, subgroup of a finite group G always divides the order of G. That's why this index is in fact order of S3 divided by the order of this normalizer of A in S3, so which is equal to 6 by 3, which is equal to 2, and you know this is equal to order of CA. You know very well that CA is containing two elements, we already have discussed in detail, and now this is another way to find the number of elements in a conjugacy class, and we want to find that how many conjugacy elements, how many elements in its conjugacy class. The idea is to find its normalizer. You can find normalizer of A in S3, and you know that those elements of S3, which commute with A. So you know that E, A and A square are the only elements which are commuting with A. That's why, so its normalizer of A is E, A square, and you know then you need to find index of normalizer of A in S3. Index in S3 is equal to, by Lagrange theorem, you know very well, Lagrange theorem says that the product of index and the order of a subgroup is in fact the order of G. You know here order of G must be finite. So that's why index is equal to order of, by order of the normalizer, which is equal to 6 by 3, which is equal to 2, which is equal to order of CA. So the number of elements in a conjugacy class, that's why you have we have this theorem. The number of elements in a conjugacy class CA of an element A belong to G is equal to the index of its normalizer in G. Yes, now we have verified this theorem, now we need to prove this theorem. Okay, so before proving this theorem, I have a remark, which is a very clear remark. Is, I have a remark. No, before this, what was the formula for finding the number of elements? So the number of elements in a conjugacy class, this was in fact in factorial and factorial divided by, this was the product of J Aj into Aj factorial. So if I assume that this is the order of Sn, then what this could be? Of course, this is the order of the normalizer of A, or you can say the order of the centralizer of A. So, according to this theorem, this is in fact order of Sn divided by, this is A, the number of elements in its the number of elements in a conjugacy class is Ca of an element A is equal to the index of its normalizer. Index of its normalizer. So to write index, here should be the order of. Here should be order of n Sn in A. This. So what is this? This means that the order of n S3 A, the order of the normalizer of A in Sn, of this A in Sn in German, we are writing in German, is equal to product of J Aj factorial, right? And you know, since you are finding the normalizer of a single element, that's why this is also the centralizer. You can say this is also equal to the centralizer of A in Sn. This is also the order of centralizer. Okay. This is the order. So with the help of this theorem, we have another remark is that since Ca was this in my last lecture, where we have shown that with the help of this formula, you can find the number of elements in a conjugacy class as well. But here, with the help of this theorem, we should be able to know that this is in fact the order of Sn, everybody know, and what it could be, what it should be, this should be the order of normalizer of A in Sn, or you can say the order of centralizer of A in Sn. So that's why from here we can conclude that the order of the normalizer of A in Sn is equal to pi over j aj factorial, right? Which is also equal to the centralizer of A in Sn, right? Now we need to prove this theorem. Now prove this theorem. Okay, so since we want to show that the number of elements, the index of normalizer, you take suppose n is equal to n GA. This is the normalizer of A in G. You suppose this is n. Then its index. What is the index? You know, index. So index of G n GA would be equal to G n. You can use these two symbols. So what is this? This is in fact the number of right cosets. Right cosets are left cosets. So index is in fact the number of right cosets of n by in G. Okay, or you may have number of left cosets. So why not you take a collection omega where these are in fact Ng and G belong to G. Again by Lagrange theorem, we know that index is in fact the number of right or left distinct cosets, or you can say that different cosets. Okay, the number of right or left distinct cosets is in fact the index, right? Since normalizer is a group, so the number of right or left cosets by normalizer with the help of the elements of G is in fact the index of normalizer in G. So this is in fact the order of this omega if omega contains all possible right cosets. And on the other side you have Ca, and you know what is Ca? Ca means G inverse Ag, the elements of the type where of course G belong to G. Okay, G inverse A, G, or you can write G A G inverse, no problem, because G is the general element. So for sake of convenience I am using G inverse A G. So my one set is this Ca, this is the conjugacy class, and the other set is omega. If I can establish a 1-1 and on-2 mapping between these two sets, if I define a mapping from here to there and show that this mapping is well defined, this mapping is 1-1 and this mapping is onto, this means that the number of elements in this omega is equal to the number of elements in Ca. But what is the number of elements in omega is in fact the right cosets, number of right cosets. And what is the number of right coset? In fact the index of normalizer. So that's why the index of normalizer would be equal to the uh, order of this conjugacy class. And from here you can deduce that since index always divide the order of G, that's why the order of an element of a conjugacy class will also divide the order of the group G. It's a very simple conclusion. Okay. So the proof is, suppose NGA is equal to N and omega be the set of all possible right cosets right cosets. Of course, we are not writing identical cosets again and again. Omega is the number of distinct right cosets. You can write distinct right cosets of n n. What is n? N is the normalizer of Ng of A belong to G. Normalizer of n is the normalizer of the normalizer. You can write of n, where n is the normalizer of A belong to G. Okay, try to understand. I want to revise again. I want to show that the number of elements in a conjugacy class Ca of an element A belong to G is equal to the index of its normalizer in G. You take an element, then find its normalizer, then take its index. Index means number of right or left cosets, distinct cosets of that normalizer in G. Okay, this is our one set. Omega is containing all possible distinct right cosets, and the other set is Ca, which is the conjugate elements G inverse Ag of A, all those elements which are conjugate to A. And if I want to show that the order of these two sets are equal, so then I need to show a mapping from here to there, so that it is well defined, it is 1 1 and it is on 2. If I can show this, then of course these two sets are equal, means their order are same. Okay, now define a mapping. Define phi from omega to Ca by the elements of this is Ng, and answer would be equal to G inverse Ag. Of course, G belongs to G, there is no problem. Now, first at all, I need to show that it is well defined. For well defined, you know that if x is equal to y, then phi of x should be equal to phi of y, because if x and y both are same, x is equal to y, but phi x is here and phi y is here, it means that one is mapped onto 2. This is not a mapping. So that's why whenever you define a mapping, try to show that it is well defined. So for well defined, whenever I am saying that x is equal to y, we must have phi x is equal to phi y. If x is equal to y, then phi x is equal to phi y. This is the definition of well defined. Because if x is equal to y, but phi x is not equal to phi y, we say that x is mapped onto two elements, which is against the definition of a mathematical function, mathematical mapping. That's why whenever x is equal to y, we must have phi x is equal to phi y. Okay. So to phi is well defined. Number one, unit phi is well defined. So let Ng is equal to phi. Ng is equal to Ng1. This means that n g1 inverse is equal to n, and you know that it's very basic idea. If nx is equal to n, this if and only if x belong to n, you know, you are multiplying with an element and answer is n. This means that this element is absorbing in n. Mean by the closure law, you are multiplying with all the elements of it from right sides and you are getting n. This means that this is an element of n. Okay, so this means that g1 inverse belong to n. So let g1 inverse is equal to n, where of course n belong to n. This means that this implies, so g is equal to n g1, and we want to show that g inverse ag is equal to g1 inverse a g1. This is our target. Now consider we see that g inverse ag, what is the value of g? This is ng1. This is equal to ng1 inverse a ng1. And what is this? This is g1 inverse n inverse a n g1. Okay. Then again you can see that. So this n belong to n. N is the element of normalizer and normalizer of A. This means that n contains all those elements which commute with A. Since n belong to n, so n A must be equal to a n. This means that you can write A is equal to n inverse a n. So put here n inverse a n is equal to a. So this is equal to g1 inverse a g1. This means that g inverse a g is equal to g1 inverse a g1. And what is this? If you see by the definition, this is equal to phi of ng. And what is this? This is equal to phi of ng1. Of course, g1 both belong to g. So what does it mean? This means that phi is well defined. So this implies phi is well defined. Secondly, phi is 1 1. So let's try to prove this. What is 1 1? 1 1 means if phi of x is equal to phi of y, this implies x is equal to y. Suppose you have x is not equal to y, but phi x is equal to phi y. What does it mean? This. So two elements are mapped onto the single element. This is not the case for 1 1. So that's why whenever you say phi x is equal to phi y, whenever the images are equal, you should have pre-images as equal. That's why we can say that it is 1 1. So whenever phi x is equal to phi y, you should have x is equal to y. So secondly, assume let phi ng is equal to phi of ng1. So this implies that g inverse a g is equal to g1 inverse a g1. This means that you can rewrite this as multiply by this. This implies on the left side g1 G inverse A is equal to, now multiply by G inverse on the right side, is equal to A G1 G inverse. This further can be written as, if you see that, G1 G inverse and G1 G inverse. So this element G1 G inverse, of course this is an element of capital N, because capital N contains those elements which are permuting or commuting, since this is a single element here in normalizer. Those elements of N which commute with A, right? Since the set has just one element, that's why we can use the word commute. If you have more than one element, you will use the word commute. Okay, so this implies G1 G inverse belong to capital N. So this implies N G1 G inverse must be equal to N. So this implies NG1 would be equal to NG. So this implies phi of okay, right, this is our result condition. So means whenever phi x is equal to phi y, you have x is equal to y. This means that phi is 1. Also phi is on 2. You can find some elements in right coset which can have the image on the second side. Lastly, we will show that phi is on 2. So for on 2, you have omega to CA, and you need to show that for all for y belong to CA, there exists some x belong to omega such that phi of x is equal to y. If you can show this for every y belong to CA, for every y belong to, there exists some x belong to omega such that I can bold this, because omega is containing sets. Okay, if you can find some x belong to omega such that phi of x is equal to y, okay, we should write capital, because these are the sets.